For representing number of certain time. So there are several systems for representing the counting number. So generally we human being using decimal number system for the counting like 1, 2, 3. We are using this number system. But other than this number system, there are few number system more in digital electronics like binary number system, octal, hexadecimal, and there are some more number system. Common number system we generally use are decimal, binary, octal and hexadecimal number system. So you can see here the base of the decimal number system is 10. Okay. Whereas we represent by symbol decimal number as 0, 1, 2, 3, 4, 5, 6 like this. And these are used generally by humans and they are used in not used in computers. And binary some number system basis two are generally there are two symbol only 0 and 1, and these are not used by the human beings and machines also using this number system. Octal number system, the base is 8. So here we are having 0, 1, 2, 3 up to 7, and this is a number system we are not having 8 and 9. Okay, but we get we have here 9, 10, 11, 12 also. So these are not used by human beings. And another number system is hexadecimal number system. The base of this number system is 16, and we represented as a symbol like 0 as a 0, and up to 9 we represent like a 9, and after 9 10 is called as a here, and 11 is called as a B, 12 as a C. Similarly 15 is called as a F. So these are used in the computer systems and they are very useful hexadecimal number system. Now see how we called as a counting. So in decimal we call 0 as a 0, 0 to 7 just like a decimal number system. Corresponding to 0 we write it as a 0. In octal it is also called 0. In hexadecimal it is called as a 0. So 1 as a 1 here, and similarly, and in binary we call 2 as a 1 0, because in binary we follow 8421 number system, 2 1 number system. So for representing two decimal as a binary, we need to make second bit high and first bit as a 0. So 1 0 need to be represented here. Second number system is in octal we represent 2 as a 2 and hexadecimal also 2. So now you are familiar that 3 is we need for 3 representing 3 decimal as in binary we need to make 1 and 2 as a high. So 1 1 we need to write here. Okay. So 2 plus 1 become 3. So we need to put here lower 2 bits as a 1 1, and 4 as you know that we need to make the this bit high, 4 corresponding to 4 bit 100. Similarly fifth as a 101, because 4 plus 1 we need to represent 4 plus 1 here. So we need to keep fourth position bit high and the first position bit high, 101. 6 is represented as a 4 plus 2, so we need to make 110, and for the 7 we need to make high 4 to 1, all 3 bits, lower 3 bits 1 2 3, so it's represented as a 3 1. So in octal, as I already told, there are no 8 and 9 numbers because folding effect is there. So for making 8, for writing 8 decimal in binary, we need to follow the 8421 number system. So we need to make our fourth bit high and remaining all need to be placed as a 0. So in decimal when we call 8, it is equivalent to 10 in octal, whereas in a hexadecimal it is called as a 8. For the 9, we need to keep this bit high and the lowest bit high, LSB bit high, 8 plus 1 because, so we made here 1 1 high. So 10, after 10 we need to write as a 11. Similarly for the 10 we need to make 8 and 2 as a high, 8 number and 2 number as a high. So we need to write 1010 here. Okay. So the only change is date. In the hexadecimal we need to write 10 as a A. Okay. For making decimal 15, we need to write it in a binary. We need to make all this bit as a high bit because 8 plus 4 is 12, 12 plus 2 is 14 plus 1. So we need to make all the 4 bit high. So for writing a 16 decimal equivalent, we need to write it as a, not we can't write in a 4 bit. Okay. So this is the drawback of binary number system. So these are the decimal equivalents in binary, octal and hexadecimal. So it is often required to convert one number system into another number system. So we can convert decimal into octal, octal into hexadecimal, hexadecimal into binary, or we can convert binary into decimal. We can directly convert decimal into hexadecimal also. So for remembering this number conversion, we have only three methods. Okay, so you can see here first conversion, binary to octal. Okay, so we have seen that the first number system is decimal, second is the binary, third is octal, and fourth number system is hexadecimal here. So octals comes on the third position, so we have to make group of 3 bits always. Okay, so these are the binary number which we need to convert into octal. So from the lower significant digit, we need to make grouping. So this is the grouping 101, 101. Then we need to make other groups 010, that is 010 here. You can see here. And there is 1, so we need to add zeros here to making 3 bit. And we need to write the equivalent of 101, that is 5. 010 is 2 and 001 is 1. So its octal equivalent of this number is 125. Okay. Similarly, we often require to convert this octal number into binary. Okay. Okay. So converting a octal to binary, for example, we have a 257 octal into binary. So we need to write this 7 into 3 bit, which is equals to 111, and 5 as a 101, 2 as a 010, because here we are dealing in the octal and the octal position is third, as we have seen in our table also. So we need to write in 3 bits. So remember this thing. So an answer will be this one. So 257 octal equivalent is this one in binary. So both are similar. We are dealing in 3 bits when we saw the octal. Okay, this is the one method. Similarly, we often require to convert a binary to hexadecimal. Okay, so for example, we are having 1010, this one in binary, and we need to convert this into hexadecimal. So we have seen in our table that the hexadecimal position is 4. So we need to make a grouping from the lower significant digit of 4 bits. So 1011 we written here. So next is the 1101 and last one is 0101. Okay, so we need to write the 00 here also. Padding of 0 is necessary. So 1011 equivalent to B because it is equivalent to 11 in your hexadecimal number system. 101 is also equivalent to B. These are the similar. and 10 is equivalent to 2. So the hexadecimal equivalent of this binary number system, this given binary number system is 2BB. You can see here. So all this method which we have seen right now is similar. Okay. So for the hexadecimal we need to deal in the 4 bits, and for the octal we have to deal with in 3 bits. Now hexadecimal to binary number system. So you can see here in hexadecimal 25A0 is in hexadecimal and we need to convert into binary. So we are very much aware that for dealing with hexadecimal its position is 4th. So we need to write it in 4 bits. So we need to write 0 in 4 bits, that is 000. We have seen that the hexadecimal A is 10. 10. So we need to make 8 and 2 as a high. Okay, and 5 is equivalent to 0101 and 2 is equivalent to 0010. So when we write this is the binary equivalent of this hexadecimal number. Now similarly it is required to convert octal to hexadecimal. So we have seen to convert octal into binary and that binary into hexadecimal. So we will follow the same procedure, but we have seen that it hits a fractional number also. Okay, so this is in the octal number and we have to convert into hexadecimal. So first we need to convert this octal into binary. So for the fractional part we need to write, because it's octal and binary, so we have to deal with 3 bits. So we need to write 2, that is in the fractional, in 3 bits, and 7 in 3 bits. Again we need to write 5 in 3 bits, 3 in 5, 3 in 3 bits, and 6 in 3 bits. Now we need to add zeros in headers and trailers also. So for making it as a 3 bit, now we need to pair 2. Now we need to convert that binary number into hexadecimal. So we are aware that for converting a binary into hexadecimal we need to make a group of 4 bits. So we can see here we need to group 4 bits 010 for the fractional part separately and for the integer part also. 0101. So this is equivalent to 5. 1100. Okay, so this is equivalent to C. Okay, 8 plus 4, that is 12, equivalent to C. So in hexa we need to write 12 as a C. Then 1101. Okay, so 1101, 1101. Okay, this need to be write as a D. Then this 0, 1001. Okay, now these 3 bits, this is equivalent to 9, because this is 8 and this is 1, so 8 plus 1 is 9, and then 1000, that is equivalent to 1. So this is the result 19D.5C. So you have seen that we can't do here octal to hexadecimal directly conversion. So first we need to convert that octal number into binary, and that binary need to be converted to hexadecimal. Okay. So this is all these are the first procedures in which we can convert. Now the next type, I earlier told you there are only 3 types. So the second number type is when we need to convert any base into decimal. Okay. So for example, we need to convert these binary numbers, which is in the integer and fractional part also. We need to convert that into a decimal. So we need to follow this procedure, that for the integer part, least significant digit, we need to write 1 into 2 to the power 0. If we are having here octal number system, for example, we have to convert octal. So we have here base 8. So we need to multiply 1 with 8. Okay. So here we are having binary. So we need to multiply by 2. So the position of uh, this bit is 0. So 1 into 2 to the power 0. This is the first bit. So 1 into 2 to the power 1. This is 0 is on the second bit to 0 into 2 to the power 0. And 1 with 1 into 2 to the power 3. So this will become 8. 0 into 2 to the power will become 0. 1 into 2 to the power 1 becomes 2. And 2 to the power 0 is 1. And 1 into 1 is 1. For the fractional part, what will happen? It will become 1 by 2. So for 1 by 2, we need to write 1 into 2 to the power minus 1. And the next bit will become 1 into 2 to the power minus 2. So this is equals to 0.25 and this is equals to 0.5. So we need to sum all these bits. It is equal to 11.75 in decimal. So there is only, this is the second procedure in which we have to convert any base to decimal. Okay, remember this, any base to decimal. If we are having octal, so we need to multiply 8 here. Okay, we in place of 2 we need to write 8. Now third, which is the last type of conversion, that is if we need to convert any decimal number to any base. So we have to follow, for the integer part we have to do successive division method, which we will see now, and convert for the fractional part we need to do successive multiplication method. So what is successive division method and what is fractional multiplication method, we will see now. So for the successive division method, divide the integer part of the decimal number by the desired base number. For example, we are having some decimal number. We need to convert that into a binary number system. So the base of the binary number system is 2. The particular decimal number we need to divide by 2. Okay. And we need to store that quotient and remainder also. So the consider question as a new decimal, the next question as a new decimal number, and we need to repeat step 1, means we need to divide by 2 also, and we need to store the question and the remainder also until it will become 0, and we need to list the remainder in the reverse order. So we need to see this method successive division. Okay, so for example, we have to convert 125 decimal into binary. So for that we need to divide 125 by binary, because we have to convert it to binary 2. The base of the binary is 2. So we 2 6 are 12 and 2 2 are 4, and remainder will become 1. Then we need to divide again that quotient by 2 as procedure said. So we need to divide this number, it will become 3 1. So now the remainder is 0. Now we need to again divide by 2, it will become 15 and the remainder will become 1. Then again divide by 2, remainder will become 1. Again divide by 2, the remainder will become 1. And 2 divided 2, we need to divide 3 by 2, again the remainder is 1, and 1 by 2, so again remainder is 1. Now we need to do until the question will become 0. So the last remainder is 1. So now we need to read this number remainders from bottom to up. This is the procedure. Okay, we need to read. So you can see here the most significant digit will be this, and the least significant digit is this one. You can see here. Okay, we need to read from bottom to up. For example, we have to divide we are having a question in which we are having integer also and fractional part also. So for the integer part, we need to do the successive division which we have already seen. So we need to divide 12 by 2 because we need to convert into 2. So the question will become 6 and the remainder is 0. Again we need to divide and the remainder will 0. Then again we need to divide 3 by 2. The question will become 1 and the remainder is 1. Again we need to divide, the question will become 0 and remainder is 1. Then we need to read from bottom to up. So this is the answer of the integer part only. So we need to do successive multiplication on this fractional part also. Okay, so we have seen, we have not seen here the successive multiplication method. So in this we have to multiply the fractional part of decimal number by desired base number. For example, we are having here 0.625 and we have to convert into binary, so we have to multiply 0.625 by into, we have to with 2 because the desired base number is binary. So to record after multiplication, record the integer part of the product as a carry, okay, and the fractional part as a new fractional part. So we need to repeat the step 1 and 2 until fractional part of the product becomes 0 or until you have many digits as necessary for your application. Okay, so we will see by the example here. And for the successive division method, uh, we read the remainder from bottom, from bottom to up. Here we have to read carries downward to get the desired base number. Okay, so practically we will see what need to done with the fractional part here. So we need to multiply 0.625 with the 2 as the method say. So the result will be the 0.125. So the integer part is here 0 and the fractional part is 125. So we need to store that integer part here. Okay. Separately we need to store this integer part. Here we need to store. Now the new fractional part is 0.125. So we need to multiply 0.25 with 2 again. And the integer part again becomes 0 and the fractional part is 0.250. So we need to store this 0 here, and again we need to multiply 0.250 and the integer part is 0. We need to store that integer part and the fractional part is 5.500. So we need to multiply that fractional part again with the 2. Now the integer part will become 1. So unless and until we not get the integer part or sufficient number of multiplication, we need to do this multiplication. Now we need to store that number and we have to stop here. Now we need to read this part from top to bottom. So the now the most significant digit is this 0 and the least significant digit is 1. So we need to write answer together with the integer part result and the fractional part both. So this will be the result. So these are the three types only we need to remember for the number conversions. Thank you.